Welcome back, everybody. In this video, we're continuing to work with section 3.2. We're going to do one more example involving graphing a quadratic function. This one is going to be a little bit more complicated, and we'll go through all the steps really carefully. So our function looks like 2x squared plus 4x minus 3. Our first task is to rewrite f of x in standard form, or also called HK form. So let's start there. So to do that, as we saw in the last video, we're going to begin by factoring out that 2. So we'll have x squared plus 2x, and then we'll just have that minus 3 scooted over, right? So then in here, inside the parentheses, we're going to need to add a 1, right? Half of 2 is 1, 1 squared is 1. And then that change increased the right side by 2, really, right? Because if you quit right now and distributed, you'd have 2 times that red 1, which would be 2. So we're going to compensate by subtracting 2. Okay, so then we're ready to factor 2x plus 1 squared minus 5. All right, so there is our standard form. We're to find the vertex and all the intercepts. So we've gone to the trouble of locating the HK form, so we'll use it to get the vertex. So the vertex, its x coordinate will be -1, its y coordinate will be -5, and we got that from reading off the HK form. Okay, we want all the intercepts of f. So for this one, its y-intercept will be f of 0. So f of 0 is going to be -3. So we'll have the point 0, -3 on the graph. And then we also need the two x-intercepts. So you can use the original f and go from there. We already took some time to get that HK form, so I'm going to use it. So to get the x-intercepts, we need to know the x that will make the output 0. So our output is 0, and our right side 2x plus 1 squared minus 5. So we're going to solve this one. So we'll add 5 to both sides, and then divide through by 2. And then we need to take the square root of both sides. So we'll have plus or minus the square root of 5/2. We'll deal with fixing that up a little bit in a minute. That will be x plus 1. And then subtracting the 1 from both sides, x will be -1 plus or minus the square root of 5 over the square root of 2. I'm starting to work on fixing that. Usually we like to see the denominators rationalized. So we're going to do that in this case by multiplying the numerator and denominator by the square root of 2. So this will give us -1 plus root 10 over 2. Okay, writing those as points, we'll have -1 minus root 10 over 2, 0. Remember, the outputs are 0 when we're doing x-intercepts. And then -1 plus root 10 over 2, 0. Okay, so all of that was to get our x-intercepts. And then what else? Okay, so we got the vertex and all the intercepts. So now we're ready to start making the graph of f, and then finally we'll do the domain and range. So let's actually do the domain and range now to make sure I don't forget. So domain, you always want to do the domain because that's going to be the easy points, right? Input can be anything, right? So the domain will be all real numbers. Okay, for the range, we have to be a little more careful. Does this open up or down? Our original one has a leading coefficient of +2, which means that it opens upward. So it's going to have a minimum value. And so the lowest point will be at the y coordinate of the vertex, which we know is -5. So it will be from -5 up to +infinity. Right, so now we're ready to start working on making the graph. So how to scale. The minimum point is at -1, -5. So we'll need to go down to -5 and then up to like 1 or 2 would be good enough. And then for the intercepts, we need to think about this because it's going to, square root of 10 is not all that familiar, right? The square root of 10 is going to be between the square root of 16 and the square root of 9. I'm choosing square root of 9 and square root of 16 is because we know those, right? Square root of 10 then will be between 3 and 4. Okay, so -1 plus like 4 would be like -3. And just an estimate here is good enough because I'm just using it to figure out where the graph is going to go. -1 minus 4 would be like -5. -1 plus 4 would be 3. So if we go -5 to 5 in the x direction, and then -5, let's just go -5 to 5 in all directions. All right, so let me set up a grid for us to use. All right, so we're ready to finish this one up. So I've produced a grid that goes from -5 to 5 in both directions. So we're ready to put on some of our important points. I also used a calculator to help us figure out about what -1 plus or minus root 10 over 2 is. -1 minus root 10 over 2 is about -2.6. And -1 plus root 10 over 2 is about 0.6. So that's going to help us with the dots. So let's go ahead and start with those intercepts. So the x-intercepts were a -1 minus root 10 over 2. So that's -2.6 or so. The other one was at 0.6 or so. The vertex, we'll do that next, -1, -5. The y-intercept was at 0, -3. We could also use symmetry to get us another point. I know that the axis of symmetry runs through the vertex, right? And so there should be a point at -3, 1 unit to the left of the vertex. So that will give us a second point. So from there, we can kind of draw our parabola from there. I don't like that much. Let's fix it. All right, sometimes it can take a little while. There we go. I guess that'll have to do. Okay, so let's see that we've done everything that we were supposed to do. Find the vertex and intercepts. We sketched the graph. We gave the domain and range. Let me go ahead and label those points that we found. So it was 0, -3. The vertex I've already done. For the x-intercept, it was -1 plus root 10 over 2, 0. And then -1 minus root 10 over 0 over 2, 0. Okay, all right, so we've gotten everything for that one. Okay, so let's move along. So it turns out that all of these quadratic functions are going to have either a maximum or minimum value, depending on which way the graph opens. If the graph opens downward, the function will have a maximum point. If the function opens downward, it will have a minimum point. And you can tell then by looking at the leading coefficient A, whether it's positive or negative. If it's negative, it will have a maximum, and if it's positive, it will have a minimum. So it turns out we can use that just in a regular kind of math questions, and then also in some applied questions where we want to know maybe the maximum revenue or minimum cost or the minimum distance or something like that. So anytime you want to find a maximum or a minimum, for now at least, you can think of finding the vertex on a parabola. So let's try first this one. Let's say let f of x equal -x squared minus 6x plus 1. Does f of x have a maximum or minimum value? And then find it. So first of all here, I hope it's clear that the answer isn't just like yes. Okay, when we ask a question, if it has a maximum or minimum here, it means we need to choose one. And so knowing on this that the graph opens downward, that means that it's going to have a maximum value. Okay, so we want the maximum value. And then to find that, that will be the y-coordinate of the vertex. So let's begin by getting the x-coordinate of the vertex. So that will be where? Okay, the x-coordinate of the vertex is -3. To get the y-coordinate, we'll evaluate the function at -3. Okay, that looks like 10. Okay, so the maximum value is 10. Make sure that you don't put -3 as the maximum value. The maximum value is going to be a value or y value or output for the function, not the x value where it occurs. Okay, so the 10 will be the maximum value for the function. All right, so there's a little graph of our function f. Notice that, yes, the y value is at 10, the x value is -3. Again, the maximum value is 10, not -3. -3 is the x value where that maximum occurs. So what we're going to do next is look at two story problems where we use that maximum or minimum idea to help find the maximum or minimum of something. So let's try first this one. These two are both going to be from our textbook. So here it says, find the dimensions of the rectangular corral split into two pens of the same size, producing the greatest possible enclosed area given 300 feet of fencing. So anytime you're doing a problem where there's something physical going on, like building a corral here, it's a good idea to make a little sketch of what it is that you're dealing with. So let's start there. So it's going to be a rectangular corral split into two parts. Maybe they're going to separate the cows from the horses or something, okay? And it's going to be 300 feet of fencing. So we know that the area of a rectangle, we're going to need that, the area of a rectangle is going to be xy, and we know that its perimeter is twice the length plus twice the width. This one, though, has a kind of added interesting feature that there's a division in the middle, so we'll have to take that into account as well. So our 300 feet of fencing, well, let's start labeling some things, okay? X is going to be this dimension, we'll call that the height, and then Y will be the other dimension, we'll call that the width. So how are we going to use this 300 feet of fencing? The 300 feet of fencing is going to be two sides of length y, and then also three sides of length x. You should be able to tell the relationship between that and the perimeter for a rectangle formula we have above. If there were no divider here, this would have been 2x instead of 3x, but we have one divider. If you have more dividers, then that number next to the x is going to be different. So here's an equation that relates x and y, and we wanted to maximize xy. So the thing is that the area is right now a function of two variables. So what we're going to want to do is eliminate one of the variables. And we're going to use this equation, which is called a constraint, to help us eliminate one of the variables. So let's take this constraint equation and solve for one variable. It doesn't matter which we solve for. I'm going to solve for y, just to choose. Okay, so 300 minus 3x will be our 2y. So then y will be 300 minus 3x over 2, or 150 minus 3/2 x. Okay, so that is our y. So now we have the area as a function of x. It was xy, but we know that y is 150 minus 3/2 x. Okay, so we have the area now just as a function of one variable. So let me distribute to remove the parentheses. We'll have 150x minus 3/2 x squared. That x squared right there is why we're doing this in this section, okay? Notice that the coefficient of the squared term is negative, which means that if we go to graph this thing, it's going to open downward, which is appropriate for something we're trying to find a maximum for. So that's great. So we have a formula for the area. And so all we have to do is we want the dimensions, okay? That means we need to find x and y, not just the actual area. So we need to find the x and y that will maximize the enclosed area. So that will be the x coordinate of the vertex, which is minus b over 2a. So minus 150 over 2 times negative 3/2. Okay, so let's simplify that. Okay, so 2 times negative 3/2 is negative 3. Okay, so that will be 50. So our x will need to be 50, and then we have an equation that relates our x's and y's. We know that y is 150 minus 3/2 x. Okay, so that's 150 minus 75, and so is 75. So the dimensions will be 50 by 75. You need to keep track of which one is which because of the direction in which we have the divider going, right? 50 by 75 is not the same as 75 by 50. The lengths of the sides containing the divider is going to be 50. Okay, so that's it. And then to find the area, if we want it, we would just multiply the 50 by 75. All right, so kind of to recap here, because this had a geometric interpretation, we drew a picture, which was helpful. We labeled the picture with some variables. We ended up with 2 variables at first. We saw that we were able to get this constraint equation to eliminate 1 variable for us. And then we found a quadratic function whose vertex we found and used that to answer the question. Okay, we have one more. Okay, so here it says a rocket is launched in the air. Its height in meters above sea level as a function of time in seconds is given by this formula. We want to find the maximum height the rocket attains. So this will be pretty straightforward. We have a height function and we want to find its maximum. Notice the leading coefficient's negatives. That means that the parabola opens downward. We need to find that y coordinate. So the x coordinate of the vertex, I should probably be saying t coordinate, but that's okay. X coordinate of the vertex is minus 229 over negative 4.9. So times 2, right? 2 times negative 4.9. All right, so minus b over 2a. So for this, you're going to want to use your calculator most likely. So we've got 23.3673 about. Let's just say 23.367. All right, and then to find that actual maximum height, we're going to need to substitute that into the actual function again. Okay. So this will be, again, work for our calculator. Okay, so let's go ahead and calculate that. Let me work that out for you and then write it down. All right, so that worked out to be about 2,909 feet for that maximum height. All right, so this takes us finally to the end of section 3.2. We learned about quadratic functions, some of the basic features like the axis of symmetry, all of the intercepts, the vertex, which was an important idea that helped us find maximum and minimum values. And we did a little bit of completing the square to help us write functions in quadratic in HK form. All right, so let me know if you have any questions and have a great day.